let's discuss the convergence of this example. Right, now for this one also you can see that since it is of this format, you can consider this series as a power series. But see here, you have started the indexing at 1. Okay, right. Now, in order to identify whether it converges or not, we can once again apply the ratio test for this term, right? So this whole thing we can consider it as our an in the inside the series notation. So what we can do is we can just compute the limit of this one, right? Then you can see that when you write down the anth term and an plus 1th term and then get the ratio, you end up with this term, right? And then when you compute the limit, right, that is when n goes to infinity, this one will go to 0. So you are left with the modulus of x minus 3, right? So now remember, in the previous example, we were able to conclude that no matter what x we have, the limit will be infinity. But here, see, in this case, for this series, for this particular series, x minus 3 divided by n, right? For this particular series, the limit that you obtained through the terms of ratio test was this one. So now for the ratio test, in order to determine whether a given series converges or not, we need the value of that limit to be less than or greater than 1, right? So according to that, we can determine the convergence. But here, as we have a variable for x, we cannot determine directly whether this term is less than 1 or whether it is greater than 1, right? Because of this variable. Now say for example, if we use, let's have 2.5, right? If we use 2.5 for x, then this term will be let's start from the beginning. Then the series will be sigma 2.5 minus 3 to the power n divided by n. Now here it is not n factorial. The original series was given as n, right? So this will be equal to sigma n equals 1 to infinity. It starts from 1, and here it will be negative 0.5 to the power n divided by n, right? So x equals 2.5 means this series, and let's have something like let's have 5. So x equals 5 means this series, we substitute 5 instead of x, right? So you will get this one as our series, right? Now if x is equal to 2.5, then from this generalized equation or this generalized result, we can say that the limit for the ratio test will be equal to 2.5 minus 3 modulus, and that is equal to 0.5, which is less than 1. But if it is 5, that means if it is this series, then our modulus will be 5 minus 3 modulus, and that is equal to 2, which is greater than 1, right? So In other words, from the ratio test, we can say that for this value of x, the series obtained will be this one, and since the value of the limit is less than 1, the series converges from the ratio test. And for this value, the series, the limit of this ratio was greater than 1. So from the ratio test, we can say that the series diverges. So just have a look at this result and see what happens for the same series and for two different x values. For a certain value of x, the series converged, and for a different value of x, the series diverged, right? So in other words, when we have a variable for the series, we will most of the times come into a situation like this. Okay, now the very first example was a very kind of a very specific case, okay, but most of the times we end up with a situation like this. For some values of x it converges, and for a different value of x it diverges, right? So now this is the key idea that we are going to investigate more in the coming videos. It's like we have to carefully find out for what values of x that it converges and for what values of x that it diverges. Well, for this particular case, of course, as we have already computed the limit from the ratio test, we can use the conditions in the ratio test directly, right? So from the knowledge that we have in the ratio test, we can directly say that if this limit is less than 1, right? If that limit is less than 1, then the series should diverge. In other words, if this number is less than 1, then the series will diverge. Or we can say that for all the x values such that this inequality is satisfied, the series for those x values will not diverge, it converges. Sorry for this mistake. Okay, so let's try to simplify this a little further. Now, what do we mean by how can you visualize this sort of a inequality? Well, you have to know how to simplify these sort of inequalities, right? More simpler version of this one will be something like this, right? So it says the modulus of x is less than 1. So I think the easiest way is to draw a number line, right? So this says the modulus of x, or in other words x minus 0, is less than 1. So we take 0 as the center point, and then the modulus means we can go to both left and right hand side with 1 unit. So this inequality will include all the x values in this region, right? If it is less than or equal to sign, you can get the endpoints as well, right? Okay, so in a similar way you can solve this inequality as well. Now instead of this 0, you should get 3 as the center point, right? That's the only difference we have. So from 3 we can go 1 unit to the left, to the right, and 1 unit to the left. So this point will be 2 and this point will be 4. So the values of x will be in between 2 and 4, right? So for the values in this region, we know for sure, this region means 2 to 4 interval, right? So if x is an element, this is the symbol for element, right, in this set, right? This is the set starting from 2 and goes up to 4, excluding the boundaries, right? So if x belongs to this set, right, then we know for sure that this inequality is satisfied. That means this limit for such x will be less than 1. That means the series for such x will converge. Say for example, if we choose any value from this set, let's take let's have 3.5 as x, which is in this set, right? Then our series will become, now the original series was this one. Now see, previously I used 2.5, that is also within this region, right? So even 3.5, when you substitute 3.5, you will get something like this, right? So that will be the series 0.5 to the power n divided by n. So at once we can say that this series converges because the x that we chose is in the nice region. The nice region in the sense, when you choose a certain x from this region, you will get the limit for the ratio test as the limit will satisfy this inequality. So from the ratio test you can say that the mentioned series will converge. And how about the points outside this region? So when you say outside, that means all the x values that does not belong to this region. So it includes x equals 2 as well as x equals 4 and all the other x values in this region as well as in this region, right? So let's see what will happen to our series when x is on those outside regions, right? Okay, so first of all, let's consider what will happen if x is on a boundary point. So we know that we have chosen our nice region to be 2 and 4, right? So here we have 3 and here we have 2 and here we have 4, right? And let's see what will happen when we choose x equals 2, right? Then if we go back to the ratio test and if x is equal to 2, then the limit of the ratio test will be equal to x minus 3 modulus, and that will be equal to 2 minus 3 modulus, and that is equal to 1. And remember, if the limit is equal to 1 in the ratio test, the test is inconclusive. That means for this particular x value, in other words, for this particular series, we cannot use the knowledge of ratio test. Okay, but the good thing is, instead of using the ratio test for this specific x value, we can use the alternating series test, right? Remember, we have a sequence like this, and it goes to 0 and also it is decreasing. So from the alternating series test, we can say that the given series diverges. So at x equals 2, the series diverged, right? And let's see what will happen when x is equal to 4, which is equal to this one. then the series will be equal to 3 minus 4 to the power n divided by n, and that is equal to 1 over n, which is the harmonic series. And we already discussed the properties of harmonic series. And also now here, if x is equal to 4, again the limit of the ratio test will not work, because the limit of the ratio test is the modulus of x minus 3, and that is equal to 4 minus 3, which is equal to 1. So the test is inconclusive for x equals 4 as well. But if we just directly compute, or if we directly see what will happen to our series when x is equal to 4, you will obtain the harmonic series, and we know that the harmonic series diverges, right? We have already done this fact. Okay, so at x equals 4, the series diverged. Now see, in this region we say that the series converge, and at x equals 2 we proved that the series converged, and at x equals 4 we say that we proved that the series diverged. And how about the remaining x values in this region as well as in this region? For these outside regions, we can once again go back to the limit of the ratio test, right? So the limit of the ratio test, we obtained it as this one. Okay, and if it is like this, we say that the series converges, and from the ratio test itself you can conclude that if the limit is greater than 1, then the series diverges. So we just have to let's see what will be these values, right? So that means if we consider this as the center point, here it says the x values with the modulus. Now this modulus is like something very similar to the distance. So here it says the distance of x to the point 3 is greater than 1, and here it says the distance of x to the point 3 is less than 1. So distance means, if it is just 1 unit, that means if it is 2 and if this point is 3, all the points in this region, if you take the distance, like whatever the point you choose in this region, the distance between that point and 3 will be greater than 1, because the distance 1 is represented by the number 2. So all the numbers on the left side of 2 will have a distance greater than 1. In other words, this inequality will be true for the values in this region, and that is also true for the values in this region as well, right? Because the distance between points in this region with number 3 will be greater than 1. Okay, so for all these points, this inequality will be true. In other words, for all these points, if you substitute in the series, the limit of the ratio test will be greater than 1. Say for example, if we choose number 10, and then if we use number 10 as the value of x in our series, that is 10 minus 3 is 7 to the power this one, we don't have to manually calculate the limit of this one, because from this generalized notation we have the result. We already have the result, right? So, and it is the same for these numbers as well, right? So hence what we can say is in this region as well as in this region, the limit from the ratio test is greater than 1. In other words, the series diverges. Right? Now see, we have predicted or evaluated the convergence or the divergence of the series in the whole number line. Right? This is the convergence of this series in the whole set of number line. Right? The reason for all these things is because you have a variable x in here. Right? So what you should identify in this video is that when you have a power series, that is a series with this variable and of this format, when you have a power series, it might not converge for all the values of x. Right? It will converge for certain values of x and it will diverge for a certain values of x. Right? And we have the tools, we already have the tools to find the values of x that this series converges and the values of x, and to find the values of x that the series diverges. Right? And there is kind of a theorem to precisely mention this statement for the convergence of or the divergence. I will discuss it in a later video, but just for the time being, what you have to identify is that when you are given with a power series, there are some specific values of x which will do a different job. Right? So for these values of x, it will converge, and for these values of x, it will diverge. Right? And also there is one more thing that you should notice. Right? Here the power series or this series did not have a property like this. Right? It's like for a certain values of x it converges, and here you have a gap, and then another set of values of x it converges. Like this, it will not have such a property. Okay? It's like if it converge, it will converge throughout a certain interval and it diverges in the remaining parts. Right? This power series did not possess this sort of a behavior. It's like the converging points are like all the converging points are packed together. Right? So this is a very important property of like it's a very important and a common property for all the power series. Right? None of the power series will possess this sort of a behavior. Right? If it converge, then all those converging points will be packed together, and in the remaining regions it diverges. You don't have any holes in between. Right? So it converges throughout a certain region, and outside that region it diverges. It will not have these sort of converging regions. Right? Like here you have a hole in between. It does not have such a property, and it is a common thing for all the power series. So there are, like in this video we discussed a very very important property of power series. Right? So I will repeat that one more time. When you have a power series, you can find the x values where the power series converges and the x values where the power series diverges. And for these converging x values, it possesses another beautiful property, and that is it will converge throughout a certain region, and outside that certain region it will diverge. This converging region will not have holes like this, right? So that is very, very important, and from this you have another name for these regions, and that is called the interval of convergence, and there is another thing called the radius of convergence, and I will discuss it in the coming videos, right? Okay,